Welcome to a new video in a course on the Riemann hypothesis and its applications. And this video will be a bit of a digression where we discuss the functional equation of the Riemann Zeta function. So in the previous video, we broadly introduced the Riemann hypothesis and we defined the Riemann Zeta function by its functional equation. So the goal of this video is to prove the functional equation of Zeta. So let us start by just recalling a definition from complex analysis. If you have a function that is analytic and it's defined on an open set U, and say we have a set open set U, and we have another open set, say V, and say we have F defined on the smaller open set U. Then a function f that is defined on V and that equals f, that equals little f on U, is called an analytic continuation of f. So if f of z is equals to little f of z for every z in U in the smaller set, then we call big F an analytic continuation of little f. So to prove the functional equation of the Riemann Zeta function, which is the analytic continuation of the known Dirichlet series with coefficients equal to 1, we will need to prove a functional equation of gamma, which is an easy thing to do. So let us just do that. And the reason we want to discuss the gamma function is that it appears in the functional equation of the zeta function, which we're going to see in a few. So the gamma function, I remind you, it's defined as an integral of the integrand e to the minus t, t to the s over t dt, and this is defined for the real of s strictly bigger than 0. So so it's defined everywhere in the right half plane, right half complex plane, and we wish to continue this. We wish to define the gamma function elsewhere. We wish to define it for negative, complex numbers with negative real parts, and to do that we will need to analytically continue the function gamma to the whole complex plane, but it turns out we can't do that. We can meomorphically continue it to C except for poles at 0 and then negative integers. So let us see how we can do that. So we're gonna prove that the gamma function has the functional equation gamma of s plus 1 is equals to s gamma of s. And this is really an easy integration by part task. So let us see how to do this. Well, gamma of s plus 1 is equal to the integral from 0 to infinity of e to the minus t, t to the s dt. So it's going to be t to the s plus 1 over t, so it's t to the s. And then we simply integrate this by parts. And what do we get? We get minus t to the s, e to the minus t. This is between 0 and infinity. And we're gonna have the other integral of s t to the s minus 1, e to the minus t dt. And it's quite easy to show that this is 0 and this is just s gamma of s. So via this functional equation, one can continue gamma to the whole complex plane except at 0 and the negative integers. And to see this, let me just show you this real quick. So the gamma function is defined for the real of s strictly bigger than 0, so it's defined on the right half plane. And say we wish to continue the gamma function to complex number to the right of the line real of s equals to negative 1. And to do that, we notice that gamma of s plus 1 is equals to s gamma of s. This is the functional equation. So we may define gamma of s as gamma of s plus 1 over s for s not equal to 0. So the gamma function is defined for, so now we have the gamma function is defined for s, for the real of s strictly bigger than 0. So this right hand side is defined for the real of s strictly bigger than -1, except for the problem at s equals to 0. So we could analytically continue gamma, because we could define gamma in terms of another function that is defined on a bigger set, and it's analytic there. So we analytically continued gamma to a function that is defined for the real of s strictly bigger than -1 except at 0. So we analytically continued gamma to this set except at 0. So at 0, there is a problem, but it's really a simple pole. And why is that? Because, well, gamma of s plus 1, if we evaluate it at s equals 0, this is just gamma of 1. And this is really 1. So it's well defined there. This gamma function is defined at 1, and it's not only defined, but it's also regular. It's analytic at 1. So at s equals 0, this function on the right, it has a simple pole. So in this way, we could continue the gamma function to the real of s strictly bigger than -1, and you may repeat these steps and continue it to the whole complex plane except the negative integers. For example, you may continue it to the real of s bigger than -2, for example, via this equation. So it's gamma of s plus 2 is equal to s plus 1 times gamma of s plus 1, which is s plus 1 times s times gamma of s. And in this way, you can define gamma of s to be gamma of s plus 2 over s times s plus 1. So the right hand side is defined for the real of s strictly bigger than -2, except for poles at s equals 0 and s equals -1. So in this way, we may analytically continue the gamma function to the whole complex plane except the negative integers and the 0 and s equals 0. So now we're ready to prove the functional equation of zeta. So I remind you, the Dirichlet series with coefficients 1 defines the zeta function for the real of s strictly bigger than 1, because by elementary calculus, this is just a p series, and it's convergent for those real s with that are strictly bigger than 1. And it's a well-known fact from complex analysis that such a function, if it's regular for some real number here, for example, that is strictly bigger than 1, then every wedge of the shape, so if you look at this line, then any wedge that is contained in here, you will have that the function is regular over here. So this function is really defined for the real of s strictly bigger than 1. Now, the question we're asking here, can we define the zeta function elsewhere? Can we define it over here, over here, over here, over here? Because as I mentioned in the last video, the Riemann hypothesis is really a statement about the zeros of the Riemann zeta function lying on this line, like lying on the critical line. But how are we able to talk of zeros of zeta on this line if it's not defined there, right? So we want to prove that it can be defined there, and in fact it can be defined everywhere except for the pole at 1. So this is the goal. But before we attempt to prove that it's actually it can be actually continued to the whole complex plane except at 1, so it can be continued to here, let us try to prove that it can be continued to this strip, right? Let's see if we can define it over here. So to be able to continue zeta to the real of s strictly bigger than 0, so the right half plane is the real of s strictly bigger than 0 except at 1, we will need to recall that the alternating series defined as minus 1 to the n plus 1 over n to the s, we call this function the Dirichlet-Eta function. So this is the Dirichlet-Eta function. Okay, so this function, if you recall, for real of f, if s is real and it's strictly bigger than 0, then this function is convergent. And the eta function, we know it's an alternating series, and by alternating series test, it's actually convergent. So it's convergent, for example, for an s real over here. And in a similar way, we have this elementary complex analysis fact that if such a function is regular at this point, then you consider this line, then this function is regular on any wedge of this form, so it can be defined everywhere to the right of that point. And hence this eta function is really defined for every complex number s with the real of s strictly bigger than 0. So what's interesting is that when you add these functions up, so when you add zeta, the zeta Dirichlet series and the eta Dirichlet series, when you add these up, you get some terms, you get the odd terms cancelled, and you get the even terms accumulating to add up to 2 terms. So this is for n bigger than or equal to 1. And what is this? And what is this? This is really 2, and you pull the 2 to the s from the denominator, and this is just zeta at s. So the sum of zeta and eta is this factor times zeta of s. But what does that mean? Well, this means that you may define zeta, so you may choose to define zeta as, if you rearrange the terms, this is going to be 1 over 1 minus 2 to the 1 minus s times eta at s. Now, why are we doing that? Because remember, we are analytically continuing zeta, which means we have to have a function that is defined in a bigger region than the region where zeta is defined. And we want equality to happen for every value where zeta is defined, because this is the definition of analytic continuation. So we've just written zeta as a function that is defined not only for the real of s strictly bigger than 1, but also for the real of s strictly bigger than 0, except for s equals 1, where there's a problem here. So so this function on the right is regular for the real of s strictly bigger than 0, and hence we've just analytically continued zeta to the right half plane, except for a pole at s equals 1. So in this way, we've just analytically continued zeta to this half plane except at s equals 1. So the next harder question, in fact, is how can we define zeta, or how can we analytically continue zeta to the left half plane, including the line real of s equals to 0. So this is a little bit of a harder task to do, but it's not that bad. So let us head into that. So again, can we do better? Well, of course we can. We can define the Riemann Zeta function on the complex plane, except for a pole at 1. So what is the idea? The idea is that you are trying to derive a functional equation of the zeta function. So one way to do this is to use some known functional equation. So to use some functional equation of a function that appears in the definition of zeta, so that you can analytically continue zeta to places via the functional equation of that function. And when you study zeta functions, functions that tend to appear to be related to these are what's so-called theta functions. So theta functions, I'm gonna tell you what these are. I'm gonna tell you what these are, and we're gonna talk about their functional, the functional equation of the theta function that we're gonna need. Let us first discuss where this theta function is coming from. So remember, to study this zeta function, we want the term n to the 1 over n to the s to appear. So it turns out that this comes up naturally from the definition of gamma. And the reason is, let me just discuss this here briefly. So if you look at the gamma function, gamma of s defined as the integral from 0 to infinity e to the minus t, t to the s over t dt. And if we just do a simple change of variable here, if we just send t to the to nt, here's what we get. We get the integral from e to the minus nt. We're gonna have n to the s coming from here, so let's put it outside, and the n from here and the n from here will cancel each other's, so we'll be left with this function. So what we could do is that we could obtain a function of this form. So we could let the n to the s appear using the gamma function, and we may rewrite this a little bit. So we may rewrite this as 1 over gamma of s, and there's a 1 here. So if you just look at this, what you can immediately do is sum this up, and you will be getting the zeta function on the left, and you'll be getting some other summed function on the right. If you sum this and you interchange the sums and integrals, because you can do to the exponential decay of the integrand here, so you will get this form. You will get zeta of s is equal to 1 over gamma. The integral, when you sum this up, you will have this gamma function appearing here, and you'll be having t to the minus s, t to the s minus 1 dt. So from here, one can try to work with this function, and it's just a geometric series, so one can try to play with it. So there's a nicer proof, in my opinion. You see, like, instead of starting with n, so instead of sending t to nt, what we may have done is that we may send t to n squared times t. So if we do that, what we'll be getting is, instead of 1 over n to the s, we will be having 1 over n to the 2s, and 1 over gamma the same, and then we'll be having n squared here, and the rest is the same. So if we now sum things up, if we now sum this up from n equals 1 to infinity, we will be getting zeta at 2s, because remember, zeta is defined as, so zeta at s is defined as 1 over n to the s. So if we put 2s here, we'll be getting n squared, or n to the 2s in the denominator. So if we sum this up, on the left, we're gonna have zeta of 2s, and on the left and on the right, we're gonna be having this integrand showing up. Now, this proof is due to Riemann, and Riemann noticed that when you play with zeta as such, you get something called a theta function. So this is defined as theta, the sum from n equals 1 to infinity of e to the negative n squared t. So this is the theta function. In fact, Riemann defined this up to a constant. So what he did is that he just sent t to pi t. So in this way, you will have a pi t here, and this change of variable will lead to pi to the s over 2 coming out, with the Jacobian cancelling with the 1 over t over here. So long story short, what we're saying here is that if we define the theta function as such, it turns out that it's easy to obtain a functional equation, or what's so-called a modularity of the theta function. And we can use that functional equation to obtain a functional equation of zeta. But let us see. So here we have zeta of 2s. How do we get to zeta of s back? Well, you can easily send s to s over 2. So if you do that, you will be having zeta of s here, and you'll be having this s over 2 coming from this s over 2, and you will be having gamma of s over 2, and the rest is the same. So so what I'm trying to say here is that you could just write zeta in terms of theta, and you know something about theta. It's easy to derive a functional equation of theta. It's not very easy, but it's relatively easier. So it's easy to derive a functional equation of the theta function, so one can use that to obtain a functional equation of the zeta function. So so before we continue with this, let us just make an observation here. So this theta function, excuse me, I should have defined it over z. So this theta function is in fact defined over z. So just a bit of a notation here. So this theta function is defined over z, and hence this term showing up is just theta at t negative 1. Why negative 1? Because the constant term for n equals 0 is 1. So you have e to the 0, which is 1, and you have the theta function defined as such. So so you can define zeta as a function of theta. It's in fact theta of t minus 1 over 2. So so before we discuss the functional equation of theta, which we won't prove, it's just an easy application of the Poisson summation formula. So before we discuss that, let me just turn your attention to a very nice thing here, is that if you look at theta of t minus 1, you can write this as 2 times, or maybe let's divide by 2. So 1 over 2 times that is equal to the sum of e to the minus n squared pi t, as n runs from 1 to infinity. So as t goes to infinity, this function has an exponential decay, and hence it's nice. I'm gonna define what I mean by nice here, but let us just do a little bit of a digression here and discuss, or at least let me just tell you what the functional equation of theta is. So I guess I have this written here somewhere. So so it turns out that it's easy to prove the following functional equation of theta. So the square root of t, theta of t is equals to theta of 1 over t. This is for t positive. So how do we prove this? Well, I remind you of an elementary theorem in Fourier analysis. If you have a function that is smooth enough, right, and it has a certain decay at infinity, it has a nice decay at infinity, then what's going to happen is that if you sum the function over all the integers, it's the same as summing the Fourier transform of that function over the integers. So the reason this is pretty nice is that so the theta functions usually take form similar to this one, and the Fourier transform of this thing is easy to compute. You just evaluate the integral of the Fourier transform, and it's quite easy to show that if you have function of the form e to the pi a x squared, and you compute its Fourier transform, then you're gonna just pull a term. This is called the Fourier transform of the dilation. You're gonna just pull a term, which is a to the negative half, and you're gonna be dividing instead of multiplying by a. Now, what's interesting here is that this term, which is the square root of t, is justified by this a to the half. It's justified by a to the negative half. And when you arrange terms, since like this one is just e to the minus pi ax squared, and when you evaluate it at n, this is going to be n squared. And the Fourier transform, it has the similar form, but except instead of multiplying by t, you'll be dividing by t. So this justifies the 1 over t appearing over here. So keep this functional equation in mind, because this is the thing that we're going to use. I'm going to remind you of this, but the thing is, if you multiply theta of t by the square root of t, you just get theta of 1 over t. So this is the functional equation of the theta function that we defined, and enough, in fact, to continue zeta to the complex plane except at 1. So let us see how to do that. So if we rearrange this, if we bring these to the left, and we rewrite this last equation, we have pi to the negative s over 2 zeta of s gamma of s over 2 is equal to that integral. So if you look at this integral, there are actually two problems. So there is the problem at infinity, and there is the problem at 0, right? Because what is this? This is t to the s over 2 over t. So there is a problem at 0. So we're gonna see how to resolve these problems. So the idea is that you resolve one problem at a time. So let us write this integral as an integral from 0 to 1 plus an integral of 1 to infinity of the same stuff, right? So if you look at the integral from 1 to infinity, let me just discuss this here. Let me just discuss this in a bit more details. So if you look at the integral from 1 to infinity of theta of t negative 1, t to the s over 2 negative 1 dt. So this has no problem at 1. The only problem is at infinity. So here's the niceness of the theta function comes into play. So I remind you, if you look at this function, it's equal to this sum, and this has a nice decay as t goes to infinity. And so you have a function that is so you have a function over here that has a nice decay, and you have a polynomial, and thus this integral is nice and it's regular, and thus this integral is defined for any s. Like it's literally defined for it's literally defined for any s. Like it's defined for any s in C. So it's a very nice integral due to the rapid decay of this function. So now it suffices to discuss the niceness of the integral from 0 to 1. So if we could discuss this integral and discuss where it's defined, we will be wrapping up the discussion on the functional equation. So let us discuss this integral and to see what's happening here. So before we do that, let me remind you that the theta function has the functional equation square root of t times theta of t is equals to theta of 1 over t. And why is this useful? Well, the reason this is useful is that via some change of variable, what you can do is that you can change this integral from an integral from 0 to 1 to an integral from 1 to infinity, because when you have this change of variable t to the 1 over t, you change the boundaries and you get that. So you can resolve the problem at 0 by passing to a change of variable. And so if you apply this change of variable, you will be having here some 1 over t squared term, and you'll be rearranging the terms over here and the signs, and you'll so there is a 1 over t over here. So if you look at this integral, so let us discuss this integral aside here. So the integral from 1 to infinity of theta of t, theta of 1 over t minus 1, and allow me to write here some it's some polynomial, dt. What is this? This is equal to the integral from 1 to infinity. Let's use this functional equation. It's gonna be the square root of t theta of t negative 1 times some poly dt. And what is this? This is like you rewrite these terms. So let's rewrite these to infinity theta of t. You just separate the integrals times some poly dt minus the integral of some poly dt, and this we can evaluate. It's just an elementary integral to evaluate, and this thing here, it's not nice yet, because remember, we don't know much about theta of t, but what we know much about is theta of t minus 1. So what we're gonna do is that we're gonna subtract and add a term. I just include it in this polynomial. So this is gonna be theta of t negative 1 times some poly prime, it's a new polynomial, dt, and then we're gonna be adding, because we subtracted this term, we're gonna be adding the integral of a polynomial, and we have the subtraction of another integral of a polynomial, and these things we can evaluate. These are just easy things to evaluate. This thing over here is okay because this has a nice decay, and this is just a poly, so this is okay for every complex number s, because this remember this polynomial that we've just called poly, it's just a polynomial, a function of s2. So this is defined for every s. This is okay for every s. And what remains to discuss is whether these polys are okay, or these integrals are okay, and if they are okay, where are they okay? So if you evaluate these integrals, what you'll be getting is, let me just fix this here. So if you evaluate these integrals, what you'll be getting is theta of t, as we got, minus 1 times some polynomial, and this is good for every s. So this is good for every s. And if you evaluate the integrals of the polynomials, which are easy to do, you will be getting a term which is 2 over s minus 1 and 2 over s. So this is all to say that this integral, it's a little bit of a mess now. So this integral, just use the yellow. So this integral, if we split it to an integral from 0 to 1 plus an integral from 1 to infinity, this integral is okay everywhere, right? This integral is okay except at s equals 0 and 1, because there's a problem here. So there are simple poles. So so this whole function that we have over here, which is pi to the s minus 1 zeta of s times gamma of s over 2, this whole function is okay everywhere except at s equals 0 and s equals 1. And by the way, this function is called the completed zeta function, and it's called xi, right? So what did we just do? We just proved that the function pi negative s over 2 gamma of s over 2 zeta at s, this function is okay everywhere except at s equals 0 and 1, right? However, I remind you here, there's an elementary fact about the gamma function, which is that the gamma function has no zeros. It's never zero, right? And not only that, the gamma function has a pole at 0, right? So so this is never 0, and it has a pole at 0. So if you define zeta by the stuff that we got on the right, which is the integral from 0 to infinity after we opened it up and discussed what it is, divided by pi to the negative s over 2 gamma of s over 2. So this zeta function, defined as such, is a function that is defined everywhere. We just analytically continued the zeta to the whole complex plane, except for one problem at 1, because the problem at 0 is already taken by the gamma function. So so in this way, we've just analytically continued zeta to c negative c remove 1. And there is just one more step to wrap up this video, which is what is the functional equation of zeta, right? So if we call this function xc, because it's called the completed zeta function, it's called xc. If we call this function xc at s, let's say xc at s, right? So if we have, it's pretty easy to say that xc at s is equal to xc at 1 minus s. And why is that? We just evaluated what xc is. Well, xc is this thing, and it's the integral of this whole thing from 0 to infinity. If you split the integral, you get two things. First of all, you get this thing. You get this integral from 1 to infinity. This is the first bit, and the second bit is this thing. But what is this thing? It's this whole thing here, right? So there's a very nice observation now, which is that if you send s to 1 minus s, if you look at the sum of this of this thing plus this thing, and if you send s to 1 minus s, you notice that this doesn't change. This is invariant under the function s goes to s minus 1, to 1 minus s, excuse me, because you see that these two terms remain the same if you send s to 1 minus s. And this integral, if you send s to 1 minus s, you will be getting this integral. And if you send s to 1 minus s in this integral, you'll be getting the integral below. So this function is invariant under the map s goes to 1 minus s. If you evaluate it at 1 minus s or at s, it's the same. Thus, this function has this functional equation. And from this functional equation, you can easily get a functional equation of zeta via some reflection formula of the gamma function. So let me just write the functional equation of zeta to wrap up this video. It's going to be gamma of s over 2, pi to the negative s over 2, gamma of s over 2, zeta at s, this is equal to pi to the negative 1 minus s over 2, gamma of 1 minus s over 2, zeta at 1 minus s. And this defines the functional equation of zeta. And in the next video, we'll be discussing some applications of the Riemann hypothesis.